So this is Sctp in Wireshark. This packet capture, along with many in this video series, is taken directly from wireshark.org. They have actually a packet capture repository for a lot of different good example call flows. So this is actually one that you could even look up and take for yourself, sctp-addip.cap. First packet, just to look at the protocol stack, it's IP, then Sctp, transport layer protocol. Source and destination port numbers. Same concept as TCP and UDP. Verification tag, I don't believe I mentioned in the first video. This number is going to be, well, it's a 0 in the first message, but you're going to see that change in cookie echo, and init ACK is going to have the other sides. What this is a one-way identifier for the association from the endpoint. So if you've got multiple paths from a single endpoint, between that endpoint towards another for a common association, you're going to have a common verification tag number. So I'll skip over to the others here. So verification tag number 71B8-1D1F. If I apply that as a filter, you'll see that that's every message sent from 192.168.0.100. Also note that if that endpoint had multiple IP addresses, they would be using, from that same IP address, anything with this association would use that verification tag as well. So that tag can be useful, especially if you've got multiple associations. If your redundancy model actually includes multiple Sctp associations between the two endpoints, you might actually have multiple verification tags and a need to parse by them. So init echo, I'm just going to do a little bit of packet dissection here. So checksum field, the chunk type is init. Init will be 1. Data be the most common, really would be a 0. Selective ACK would be 3, I believe, yes. Init ACK would be 2, yes, and I believe 10 and 11 for cookie echo and acknowledge, yes. So init, as you go down chunk flags, let's see here, initial verification tag number, advertised receive window, here we go. So advertised receive window, as I mentioned before in the previous slides, this is a 32-bit field, and you will not see any window factor or window scale factor here. You're not multiplying it by anything. It's large enough to sort of stand on its own, unlike TCP. So if I did not have this four-way handshake, let's say I started with this data and this selective ACK, the ACK itself is going to have the advertised receive window field, and that on its own, even if you did not have the handshake captured in this trace file, would be enough to drive the actual window size. Again, unlike TCP. So as you continue down, stream numbers are negotiated in the init and init ACK. Initial TSN. So, okay, here's one. In TCP, this is sort of a different specific to Wireshark. In TCP, Wireshark supports a feature called relative sequence numbers, where you take this large TSN number, which always starts out as a relatively random number, and then they start incrementing it based on data that gets sent and received across the session. With TCP, you can set that to 0 in Wireshark by default. That feature is not available, at least as of Wireshark 1.10.1 for Sctp. You're stuck with sort of the large number, and you have to work with sort of larger math. I believe that's 2.7 billion. 2,200,000, whatever, as opposed to starting at 0 and working up. So just a little bit harder math when you're trying to count up sequence numbers in Sctp, unfortunately. Other fields, so you've got advertised parameters that this side supports, similar to TCP, where you've got options fields to say what sort of extra add-ons to the protocol that you support. Here he's declaring his IP version, which they have to advertise at the beginning so that one side doesn't try to send IPv6 information to something that only supports IP version 4. ECN is explicit congestion notification, and they're advertising those parameters. And forward TSN is another supported parameter that he's including here. So supporting parameters. Forward TSN we mentioned before, that's the partial reliability support, where one side can say that even though it realizes that it missed a packet or is supposed to be retransmitting a packet, it can say, well, that data chunk isn't important, or let's just carry on without having to tear down the session because for whatever reason I'm not able to send that. So that's the handshake. Then as you go further down, you see more of a normal Sctp flow, where you've got data followed by acknowledgement, data followed by acknowledgement. I would say the most normal would really be data-data acknowledgement. And that's because Sctp, like TCP, supports delayed ACKs, where rather than just immediately acknowledging a frame as soon as you're able, I will actually wait a period of time to see if more data segments are coming and send a cumulative acknowledgement for 2 data segments as opposed to 1. So a more common flow is data-data ACK. And of course, if there is no other data coming, eventually a timer would expire and he would send an acknowledgement for the 1 frame. But that's the usual call flow. You also see here a case where you have 2 chunks in the same packet. So if I see in this info field SAC data, so he's acknowledging data from one side, and you see he's acknowledging cumulative ACK for TSN 270.22.00.203, and he's sending data as well, and you're going to see that that has its own TSN for the other one-way traffic counter of TSNs, and then you're going to see an acknowledgement eventually for that as well. So that's the usual flow, and then as you go down further, I realize I don't believe I mentioned ASConf. This is a way to add or change configuration of the association in the middle of it, as opposed to tearing it down and building a new one. So ASConf in this case, he is adding an IP address. Wireshark decodes this for us pretty cleanly, but so he's saying add IP address to this association. So I am a common endpoint, but you can expect to be able to send or receive data from IP address 192.168.0.102 from now on. So if you hear from him with this verification tag, this is this association with this port information. So he's part of me as an endpoint, and that's what it's sort of sending. And then here you see an acknowledgement for that. And I believe there's another because this scenario is called add IP address. So here he's not only adding an IP to the association, here he's changing the primary. So if you go down, IP address parameter, set primary address parameter. So now we're saying primary address 192.168.0.102. Again, with this guy as the endpoint A, 192.168.0.101. He's saying new primary is 102. And if you catch this, the acknowledgement is actually sent to 102, not to 101. He's talking to the same endpoint, but he's acknowledging what the new primary is, which is kind of cool. And you see he's still sending data from 101 and getting it acknowledged successfully. 101 acknowledged. You see, with Sctp, you actually are able to really send data over any path that's needed, and the other side should be able to support it, even if it's not, as you see, the designated primary. Then as you go down here, you're going to see a deletion procedure, so remove this IP address from the association. So it started as 101, 102 was added, 102 was set as primary, and now 102 is removing 101. So you go back to having a 1 IP to 1 IP association of 102 to 100 with the same verification tag. In fact, if you take this one and apply as column, apply as filter, what am I doing? Apply as filter, you see the same verification tag was used for the 101 communication as 102, so it's the same association, same endpoint, different IP address and different path. And then you see the shutdowns. There's actually an extra message here. I'm not sure why. It might have been a time waiting for the other, but usually the sequence would be shutdown, shutdown acknowledgement, and shutdown complete to end the association. This would be roughly the equivalent of fin, ACK, and acknowledgement as a final acknowledgement. And the same rules apply for fin, I believe I mentioned before, but if you send a shutdown, the other side is actually allowed to continue sending data, and you should be able to acknowledge it while the association is being gracefully shut down. It could, in theory, continue indefinitely, actually, with one side sending after the other side has already declared that it is done. This doesn't on its own, a shutdown does not on its own end an association. An abort, on the other hand, is basically one side saying, we are done. It's like an RST message in TCP. So for Wireshark Profiles, for sort of troubleshooting Sctp captures, I usually don't make a specific profile for Sctp. I do for TCP. Sctp I find, just for one reason or another, there aren't a lot of columns that I always need, as opposed to TCP where you always need SYN and you always need acknowledgement, you always need your timing. Sctp doesn't quite support those as well as TCP does, and I sort of have to go through other methods. We'll talk about that in a little bit here. But what I do is set up color rules. So this is sort of what I have. I usually have one very simple kind of aggregate color rule in orange and blue, just because it contrasts with all the existing color rules in Wireshark to show anything that is either wrong or bad or unusual, or something that I would want to be paying attention to usually if I'm troubleshooting a protocol. So for Sctp, I do it mostly just on chunk types, and error chunk as well, and error chunk types. I'll talk about that in a little bit. But here you've got the shutdown sequence in orange. Association is being shut down. That might be something you want to be aware of. And I also have the inits. Now, from the description I just gave on something that is wrong or unusual or something I want to be very aware of in a trace if I'm troubleshooting, you might wonder, at first at least, why I have inits and initial session setups as something that should be considered wrong. Well, consider this. Sctp, its main use is in really telecommunications. So it's meant to serve signaling protocols between pieces of important network infrastructure. So this would be the enterprise equivalent of a TCP session upon which your BGP neighborships are built between your IP routers and those of your upstream internet or WAN service providers. That TCP session, it's not like an end user TCP session towards the internet where you're used to seeing a session on a web browser created and torn down, the TCP through a handshake happening with fins and RSTs constantly through a normal baseline trace of a normal end user. It's not like that at all. In this case, Sctp for the most part is always on, and you would only usually be seeing inits or shutdowns during a major network event or during a maintenance window if you're building something new. Other than that, in most cases, I would say an init packet is a very bad thing, because it means most likely that something was torn down or that someone is building something brand new. And if this is part of your critical network infrastructure, you want to be very aware of whenever either of those two things are happening. Hence the color rule. So just to show a few other packet captures, I'll give some examples of some of the tools that Wireshark has for Sctp specifically here too. I'll open a diameter trace. This was meant to highlight an init and abort message. So this is that RST equivalent, chunk type 6 abort. It's a pretty small message. It's really conveying most of the same information that a single bit in Sctp or in TCP was conveying, that one little RST flag. In abort saying no. So here in init abort, this is like TCP SYN RST. This could mean that endpoint or that IP address is not configured on the other side. I would say with Sctp, again, because it's more for network infrastructure and not end users and not serving many subscribers, let's say, Sctp systems are more likely to have an implicit deny approach to new sessions being created, even on a port that it might have open. The equivalent of a TCP wrapper, deny everything, and then you'd manually configure what associations and paths you want to actually plan out and build. So if there's no configuration, init abort will be a typical response that I would expect to see from most Sctp speakers. So in this case, we're carrying diameter. That will be a very common application to run over Sctp. Diameter would be a big one. Anything that's MTP carrying, message transfer part for SS7 over IP, that would also be a very common application to run over Sctp. So let's go to Sctp for a second, and you'll see actually some of those applications map things that would run over MTP. We'll talk about those most likely in another video, some of the mobile specific applications here. But Sctp is under telephony for, I sort of understand why, in the fact that it's often used for telecommunications, but it really should be in line with wherever we put TCP and UDP. It's a transport layer protocol. So analyze this association. This is useful. It will break down the two endpoints. You can get here as well just by right-clicking and going Sctp, analyze this association. You can write a filter that will catch the association too, and it will sort of dynamically build the large filter, which aren't necessarily, as you can see here, there's a lot of fields, so you don't usually want to get Wireshark to do that for you. It's a lot easier to write a filter for an association, especially if it's like 4 IPs to 4 IPs and they're different protocols. You could build it based on verification tags, which I think is what it basically did there. Actually, I'm kind of curious. So Sctp, probably initial Yeah, so verification tag number, verification tag not 0. Yeah, so it's basically just based on verification tags, but it's a long filter. So you don't want to have to deal with that. Usually you just want to get Wireshark to do that for you. Sorry, I was going to show you the graphs here. So analyzes association. You've got your endpoints, you've got your data chunks, as well as the number of data bytes that are being sent between the two peers. So 102 messages, 4896 bytes, 102. This is typical for any kind of a client-server application. Same number of packets. So typically request, response, and then again response typically has more information, not always, but can have more information than the request. Actually, I should correct myself. That's almost the opposite in many cases with diameter applications. Let's see here, endpoint, graph TSN. This is very similar, and it pretty much is the sequence graphs available in TCP. And this would be a case of an application that's sending a constant stream of data, really with no packet loss. So I'm not sure how easy it is to discern the red and the black in this trace. We'll just show them on their own here. So you got a few options. Show only acknowledgements, which are in red, and then show only TSNs as they increment up. Or you can show both. So if I zoom in a little bit, just draw a square and click on it, and zoom in a little bit more. Yeah, it's really hard to see, but basically right after the black is the red. So a data chunk was sent, and then almost immediately afterwards you see the red acknowledgement with the same TSN. So it just increments the TSNs and really the data chunk numbers, I believe, starting at 0 as they go up. And this is unidirectional. So if I click on graph TSN for endpoint 2, you'll see mostly the same thing in this case because this is a request and response relationship, so about the same number of data chunks being sent and about the same acknowledgement behavior. But they are two different streams. The A to B and B to A are two different streams that will be analyzed separately in these graphs, just like TCP again. Chunk statistics. This is basically just a count of the chunk types. So I think we've gone over most of these. Most of the important things. I believe there's 13 altogether that are created for DSNs, nothing ASConf, others. 13, I believe, are defined in the RFC. Correct me if that's wrong, though. But again, data is the most common, and it's usually just data, acknowledge, data, acknowledge, one or the other. Heartbeats, there are no heartbeats in this trace, but I will actually say that depending on the Sctp application and how aggressive its timers are set to, heartbeats can be set to sub-second. They can be set similar to, say, OSPF heartbeats, where they're very, very rapid, where you want to converge at layer 4 very quickly if one IP transport path fails. So you could actually have very, very large numbers for heartbeats. There are other tools for Sctp, but for the most part, they're the same information as what you just had there. So you can go and do. Actually, you can't do service response time. You can do for applications, but not for that. But as conversation endpoint lists, you do have Sctp, and we can go to it. But really, it's the same for the most part. The same information as you just had: number of packets, number of bytes, transit and received based on IP addresses. And you got 4 different IPs. And you'll notice too that you've got a terminology difference in Wireshark and in Sctp. So conversation list for Sctp versus endpoints. Endpoints in Sctp, that's 2 parts of an association. So really there are 2 endpoints in this one association. There should really only be 2 listed there, but there were 4 because it's based on IPs, not based on what Sctp would call endpoints. Just something to keep in mind in terms of terminology. But again, basically all this information is available in a much more clean and much more Sctp specific format under Analyze Association. And here you get the correct Sctp terminology mapped out. You can graph bytes, just as easily as you can graph TSNs. Data byte sent. Advertise receive window. I don't know if this is a bug or intended to work as intended, but I've never been able to figure out exactly what this is intended to demonstrate, unless I think they're just putting the receive window on the same exact graph as data numbers without like a logarithmic scale or something. Because receive window can be very, very, very large in proportion to the number of data bytes sent, especially for very small signaling protocols. I think that is what it's doing, but in this case it would be way beyond the top of the y-axis of this graph. if it is actually trying to show that. But honestly, advertise receive window, unless you've got I don't know, I don't even think I can expand it to the point where this would actually translate well. Yeah, and if I show both, if I show even just receive window, it still shows up like this. So maybe some applications this will appear by default in a more workable way, but right now, for the most part, data bytes sent rather, you might be able to get use out of this if there's packet loss or something, but the adversary receive window doesn't really present well in most cases that I've seen, at least for Sctp. And chunk statistics. So some Wireshark filters for Sctp. Went over a few of these. Sctp.sack_RTT is the time between data and acknowledgement. Yes, Sctp chunk types. So chunk types 4 and 5 are good to filter for heartbeats if you don't want heartbeats to be in your exchanges. Heartbeats, as I said, they can be very small and very easy to look past, but in some cases they can be very, very aggressive. And for capture filters, I included that as well. So Sctp is on its own a capture filter. I didn't want to include too many examples, but it's just like UDP and TCP. So Sctp, port, whatever, or not, or and not, all those operators work in capture filter syntax. Sctp and not, this I'd put just because it's a little bit. This is kind of a quick and dirty way to get rid of heartbeats in a capture file. So if you're capturing, you don't have the power of a Wireshark display filter, and you're limited to this smaller feature set, where you can't really dissect into an Sctp chunk type and say, if it's just this chunk type, get rid of it. You couldn't do Sctp.chunktype equals 4 or equals 5 or have a not on it or anything like that. So what I'm doing is this assumes an IP header of 20 bytes, and then it sort of digs into the Sctp header to the point where you have chunk type, and it takes out 4 or 5. It also assumes that heartbeat and heartbeat acknowledged do not have any other chunk types and are the first and only chunk type in the Sctp message at play. Those are a few more assumptions than most people will be comfortable with, but most of them are usually safe. Like, I don't believe I've ever seen a heartbeat message that included other chunk types. I would have to defer to the RFC, but I don't even think that is allowed. I've never actually seen heartbeat included in any other kind of message type. It's pretty much intended to be a standalone path probe. So it's a relatively safe assumption to make that heartbeat is on its own. And IP options fields are rare. I can't imagine a case where you have options fields in a connection like this. So again, fairly safe assumption, but this is just one of the easier ways I feel to sort of get rid of Sctp heartbeats, which can be a big problem and eat a lot of bandwidth actually. Even though they're small packets, a large enough amount of them can be straining on resources if you're doing large packet captures. Remember, this is for high volume telecommunications traffic. And errors, I mentioned that a little while ago. So error chunk is a chunk type that's used to convey really any of these types of errors that could happen in Sctp. I haven't been able to get good, oddly enough, I haven't been able to get good packet captures that are from a source that I am able to share in this video format that have error chunk types. But these are taken directly from RFC 4960. By the way, this table, it's a copy and paste. So invalid stream identifier. No user data. Most of these, they're all defined actually in the RFC if you want to read through it, but most of them are fairly English and self-explanatory. Invalid mandatory parameters, so protocol violation, that's simple enough. That's from RFC 4960. I mentioned RFC 2960. Basically 4960 replaces or deprecates 2960. So just one number to replace in your head, 4 instead of a 2, so 4960 instead of 2960. Doesn't always work out that way. Anyway, that is basically everything that I wanted to cover in this video demonstrating Wireshark with Sctp. I'm going to be using Wireshark in future videos for the other protocols as we go deep into the different stacks and the different 3GPP interfaces covering the EPC. This one is fairly foundational, and it's really just talking about the layer that most people don't need to think about or don't want to think about when they're dealing with the applications. But Sctp is kind of the middleman between the IP network infrastructure and all the signaling protocols that we're going to be talking about. Not all signaling protocols run over Sctp in telecommunications and not in 3GPP. There is some TCP. GTP, for example, uses UDP, even for control and call setup. But diameter is a big one for SCTP. I mentioned before, but SS7 over IP, including for historical mobile architectures that which potentially you need to interwork with the EPC. SCTP is very prevalent there as well. So SCTP is very large, and really I don't see it going away anytime soon for telecommunications. Anyway, I hope you found value in this video, and thank you very much for watching.